Hi, everyone. Thanks for tuning in to the Printed Circuit Podcast, where we will discuss trends, challenges, and opportunities across the printed circuit engineering industry. I'm your host, Steph Chavez. On this bonus episode, we're going to revisit ECAD-MCAD collaboration. As you know, this season on the Printed Circuit Podcast, we've been discussing PCB design best practices. ECAD-MCAD collaboration is such a hot topic that we've had to dive even deeper into the subject. I'm very fortunate to have guests today, Greg Arnott and Dave Walker, who are amazing, and they're going to give us their spill on their viewpoint on MCAD-ECAD collaboration. You definitely want to tune in for this. Dave, tell us about your background and how you came involved with the electromechanical design.
Yeah, hi there, Steph. Thanks for having us. So I joined Siemens over 11 years ago, 2011, having completed already over 30 years in the mechanical engineering environment across multiple industries, including consumer electronics, renewable energy, and network infrastructure. I worked in large corporates, SMEs, startups, and consultancy roles for high and low volume products, with experience in multiple different CAD systems. So now, as a senior technical software product manager in Siemens, I'm responsible for defining the direction of the Siemens NX software, focused on electronic integration and electronic and semiconductor industry.
Greg, you want to chime in and give us your background?
Sure. Good to meet you guys. Thanks, Steph. I graduated way back in 1986. I might be older than I sound, as an electronic engineer. And my career in CAD started in the 90s, working at a global division of a large printer company based out of Barcelona, where I got to partner with all of the big players in mechanical CAD at the time. The company I was working for had figured that the best way to sell plotters was to partner with the CAD companies, providing applications to the designers who would then have to hopefully print something really big with lots of consumables. From 2011, I spent some time in the solar industry. I worked out of California for a couple of years, where I launched the US operations of a Spanish solar monitoring company. I kind of loved my time in renewables. There are really good folks in that. In February 2020, I joined the product management team at Ultrasoc, which was a semiconductor debug and bring-up company based out of Cambridge, England, which was acquired eventually by Siemens, Mentor first and then Siemens in October 2020. In June 2022, I joined the Siemens NX team as a product marketing manager, so back into the world of CAD. So I'm basically an electronics engineer and marketer working in the world of mechanical CAD.
Both your backgrounds is amazing, and it's very vast and in depth. So I'm definitely talking to the right two people here when we're talking about collaborating with MCAD-ECAD collaboration. And I feel it's one of the most important topics. That's why we're diving even deeper with this bonus episode. So let's get into more of the nitty gritty here. Tell me, what is the most interesting trends in electronic design?
That's a good question. There's so many interesting things I could talk about, but I'll try to limit this to one or two or three and keep it relevant to design and manufacturing. One of the most interesting developments is what's happening in the world of semiconductors. After all, semiconductors are at the core of our electronics. Now, since the advent of the microprocessor, we've seen an astronomical increase in the compute power that chips can deliver. In numbers, we've seen a trillion-fold increase over 6 decades. That's a simply astounding increase in compute power. By comparison, if your 1965 sedan running about 60 miles an hour, if it could get you to the moon in a leisurely 155 days back in the 60s, if it had improved its performance by a similar amount like chips have, by 2015, you could get there in 1.2 seconds. And actually, that's limited by Einstein's relativity, because you'd reach the speed of light long before you could get to a trillion-fold increase. Over the last few decades, we've come to take these increases in compute power for granted, and consumers have too. Consumers simply expect their smartphones and their high-tech to keep getting faster and faster. But as you can imagine, this never-ending hunger for faster is stretching the limits of what technology itself can deliver. Now, this performance increase was predicted in Moore's law, kind of more of an observation than a law, but a lot of people like talking about it. In the early days of semiconductor technology, Gordon Moore predicted that the number of components on an integrated circuit would double every year. So the prediction in 1965, which became known as Moore's law, was later revised to a doubling of the number of transistors roughly every 2 years. So each new generation of processor would be manufactured at a smaller process node, reducing the effective transistor size. For many years, the scaling down was accompanied by a serendipitous phenomenon known as Dennard scaling. In 1974, Robert Dennard observed that power density remained constant for a given area of silicon when the dimension of the transistor shrank, thanks to technology improvements. And this observation became known as Dennard scaling. He observed that voltage and current should be proportional to the linear dimensions of a transistor. So as transistors got smaller, so did voltage and current. And because power is, it's a multiplication of the two of them, it's a product of voltage and current, power dropped by the square. On the other hand, each transistor area fell with the square of a shorter length, or to put it another way, the number of transistors in a given area increased. The two phenomena basically compensated each other. Now, Dennard scaling basically meant that with each technology generation, transistors halved in area, but they also halved in their power consumption. In other words, with every new chip generation, you could get double the number of transistors in the same area for the same power budget. Really neat. Well, Dennard scaling started to break down in the noughties around between 2004-2006 because voltage and current couldn't keep dropping while still maintaining the dependability of ICs. And the leakage current and the threshold voltage became the dominant factors in establishing a power baseline per transistor. So transistor counts within chips could still get bigger, it could still increase, but the chips would get hotter. They started to consume more power. With the end of Dennard scaling, with each new transistor generation, power density increased. And you have 100-watt kind of ICs these days. Now, the breakdown of Dennard scaling and the diminishing of performance returns that could be achieved by shrinking manufacturing processes has caused most CPU manufacturers to focus on multi-core processors as an alternative way to improve performance. When I was at Siemens EDA, also known as Mentor, I worked with an AI company in the States that was using our tech to debug a chip with over 1,000 cores. That's over 1,000 separate CPUs in a single chip, all working at the same time. Now, with the demise of the benefits available via technology shrinking, increasing performance in semiconductors will no longer rely on ever smaller process nodes or even the use of multi-cores. One thing I read recently is, talk about nanometers within ICs these days, and a nanometer is like 5 atoms of a silicon. It's an incredibly small amount. So even with multi-cores, we're reaching the limits of performance that can be achieved in 2D kind of IC design. So we believe that future performance gains in semiconductors will be driven by, among other factors, by advanced packaging flow, by stacking chips in 3D. So we're starting to see 3D chips in which ICs are effectively stacked on top of each other. And these will require advanced design packages, which will put ever more demands on mechanical CAD. Alrighty, so my second trend is engineering discipline convergence, particularly the domains of electronic and mechanical design. Now, back in the day when I studied electronics, way back in the 80s, I was lucky enough to be at a university where they recognized the importance of electrical and mechanical engineers learning each other's art. So I actually studied mechanical engineering as part of my electronics undergrad. But later, when it came to the practice of designing electronics for avionics systems, well, I didn't care that much about how or whether the electronics would fit in the final system. That was the mechanical engineer's job, something that he or she should worry about once my real work, the electronic stuff was done. So formerly, mechanical and electronic engineers pretty much worked in silos till their parts were complete. And nowadays, mechanical and electronics disciplines, they got to sync up earlier. They work better if they're integrated at every step of the way. So the smaller, denser, faster mantra associated with today's products is magnifying the importance of ensuring that electromechanical compatibility is addressed prior to the first fabrication. Waiting until fabrication, until manufacture, to validate electronic and mechanical compatibility is clearly leaving things a little bit late. The compatibility of the printed circuit board and all the associated electronic components with the housing and all associated mechanical hardware should be designed in using a correct by construction methodology. The advanced technology available with the latest design tools addresses the challenges of getting disparate engineering teams to work together by enabling multi-domain collaboration during electronic systems design, leading to shorter design cycles and improved product quality. Now, I'll touch kind of briefly on another couple of trends that I see coming up, and one of them that is very important for Siemens also is sustainability. The environmental impact of the manufacture of electronic devices is starting to get more scrutiny, as is the worldwide energy consumption of devices during their working life. So consumers, they want and expect OEMs to move towards sustainable manufacturing practices, making products that are easier, that are cleaner to produce and recycle easier. According to the European Commission, which we still care about a little bit in the UK, over 80% of a product's environmental impacts are determined during its design phase. As you can imagine, how a product is designed affects what raw materials are needed to make it, how much energy it'll use during its lifetime, and how well it can be recycled at the end of its useful life. This is an area where both electronics and mechanical design have a major role to play, and Siemens has a number of initiatives underway to help designers implement sustainable design practices and build sustainable products. And my final one I should mention is AI in electronics design. That which might be considered a product of electronics, AI, can also help design it. One of the significant challenges for efficient PCB design is the steep learning curve involved in understanding the domain and learning the EDA tools. Most engineers learn PCB design on the job. They learn from mentors, from other engineers, on their own, or by going through technical literature from the EDA companies. But understanding how and why different objects of a design are connected and how to efficiently use the design tools is rarely covered in any training. AI can help mine completed designs, that is, to go into designs which have already completed, to mine them for patterns of how tools are used, to capture that knowledge in a reusable state, in a reusable form, to either guide engineers through the design process better or take charge directly of elements of design itself. This is an area where I think in the future we'll start to see how artificial intelligence can help PCB engineers with tasks like component model creation, placement and routing, managing design constraints, and more.
I couldn't agree with you more, especially when you're talking about AI. I mean, when I think of AI as it is today, when you input constraints in a design, I look at that as a form of AI, because once those constraints are locked in, I don't have to think about it. The computer guides me as I need to route my traces or as I'm placing parts, because it's adhering to the rules. And in essence, it's following what is already its structure. And I don't need to think about it. The computer does that for me. The correct by construction is already built into it at that point. That's really hot. And I really think that is our evolution. And, I hear a lot of feedback about we'll never get to that point. That's so far in the future. And I beg to differ. I think it's fastly approaching, and those that are open to it will accelerate and advance for it and have huge success. Those that are not will drag their feet and may not be around in the next 15, 20 years because they're very resistant to change. And we see that in general overall, especially when we talk about the power and horsepower of these tools today versus the tools of yesteryear, as I like to say. As the packages are getting smaller and we think about the mechanical form factors of items, we hear a lot about the collaboration between MCAD and ECAD. And I could not stress that cohesiveness that needs to happen between those two domains and its importance. But when you think about MCAD, ECAD collaboration, what does it actually mean? Can you give our audience your vision of that?
I think a lot of development teams, engineering development teams, they still struggle to break free of some legacy practices which were perfectly good in their day but have become too old for the present day. Like people working in engineering silos with manual information exchange between teams, calling each other up, sending emails, and emails using different tool sets which may not even be compatible. So ECAD and MCAD collaboration for me means that basically, mechanical and electronic engineers, they work together throughout the engineering project to jointly bring a product to market. So ECAD and MCAD collaboration typically means that cross-domain information is shared incrementally throughout the project as changes occur. And you guys actually covered the IDX protocol and how it really helps speed collaboration by allowing incremental information in a previous podcast. ECAD and MCAD collaboration, it allows teams keep in sync and spot any errors or issues as they occur. Mechanical and electronics co-design is like an integrated approach to a system and product design that can help speed up product development by getting electromechanical projects right first time. And we find that the most successful organizations tend to take a model-based design approach. Model-based design transforms the systems engineering approach from document-centric to model-centric. So system engineers develop models of the system instead of documents, enabling the most accurate and comprehensive digital twin. And this methodology allows concurrent electronics, PCB, and mechanical design which is an integrated approach to design and verification that eliminates redundancy and rework across design disciplines. It can help reduce design iterations through product validation in the virtual domain, doing this virtually instead of waiting for physical prototypes. And reducing physical prototypes also has a dramatic effect on cost and development cycle times. So I'll give you, I think, 3 examples of why I think MCAD, ECAD collaboration is important. So I'd say an efficient and effective ECAD co-design process is important because, firstly, it increases productivity by enabling what-if scenarios. What if this happens? While at the same time allowing the engineers, the ECAD and the MCAD designers to co-design in their native environments. And secondly, it allows for, it's kind of topical, we talk about this a lot, but left shifting, it's a positive phenomenon. It allows for the left shifting of 3D collision and clearance checking into the ECAD domain. So instead of having to wait for the physical part, you can bring this over earlier into ECAD. And it helps designers achieve first-pass success by avoiding rework due to electromechanical issues that might have cropped up later, because the design intent is verified through the product development process.
Yeah, I can tell you, early on in my career as a designer, everything was done manually. Manual checks, manual handoffs, and there's so many iterations back and forth in a serial approach. And respins were like, it was expected to do 3, 4 respins that were built into the process. And don't even get me started with the legacy processes. But now in today's world with our tools and the multi-domain collaboration, you have the digital thread, a digital twin. It's amazing what we can accomplish nowadays and at a very quick pace. And correct by construction is the key, getting it right. What are some of the signs that exist for MCAD, ECAD collaboration that could be improved?
Well, we went off and we did some studies about this to get other folks' opinions and not just ours. And in a study that we got back from the Aberdeen group, we were able to see for ourselves the results of the impact of what you might call discipline convergence failure on system development teams, or that is to say, what happens when ECAD and MCAD teams are not collaborating as well as they should. And the survey found that suboptimally collaborating organizations, while they required more resources, additional resources to compensate. They missed new product objectives, so things that they wanted the product to do, but it didn't end up doing it. And they required numerous engineering change orders. And some other signs that collaboration could be improved, I'd say, are, well, you can spot it, is organizations that are still relying on the use of extra tools outside the software design suite. So they're using email, PDFs, and images and spreadsheets, or individual design teams that are missing large amounts of data that is making the use of the previous tools necessary. So can the engineer actually see copper and solder mask, etc.? Does the electronics engineer see mechanical items to help guide component placement? A couple more is like issues not being identified early in the design process or being discovered too late. You might also see a high reliance on physical prototyping, on a certain dependence on making a physical prototype. And the old one is, just unexpected project delays or cost overruns. They're all signs that collaboration could be improved.
Yeah, I can tell you every one of those bullets that you just mentioned, or those topics you just mentioned, I've experienced all of them throughout my career. And you're spot on with that. A lot of these issues continue to happen today or continue to exist today. And what really, surprises me is companies, design teams, not that they're okay with it, but it seems to be like there's no incentive to change. And they stay within their, hey, this has been the formula we've been using and this is a success we've been having and this is acceptable to us. And I feel that there's still much more room for improvement, especially when we talk about the horsepower in today's tools, what we can achieve, and we're leaving like money on the table. And yeah, it just really surprises me. But Greg, that's some great content. Let me jump over to Dave. Dave's been kind of quiet here. What is the need for successful MCAD collaboration from your point of view?
Greg has done a great job of talking about ECAD, MCAD collaboration and the pros and the cons and stuff. But I just want to take us back to basics just to make sure we're on a level set here. So I want to first confirm what we mean by ECAD, MCAD collaboration. So in the world of product design, there are different domains. Greg's already mentioned silos, different domains and different areas of expertise. But typically in today's advanced products, we have a significant amount of electronics, more so than ever before. Greg mentioned Moore's Law and the ever-reducing size, so we can put more content into the products today. Even your shoes can have tech in these days. It's amazing. So we have the electronics domain. Of course, electronics can't exist on their own. They need to be packaged and protected. This is where the mechanical design domain comes in. So ECAD-MCAD collaboration is simply the process of making sure the two disparate domains know what the other is doing. There is a third domain area of electrical wires and harness and cables and so on that we're not discussing. That's a whole different topic. We're just focusing on the collaboration between electronics as opposed to electrical and mechanical. Although the electrical is important, that deserves an entire session all of its own. So, yeah, successful electronics and mechanical collaboration. It's important that the two domains have knowledge about the state of the other. The design tools must have the capability of communicating or collaborating with the other domain, as been said. This is nothing new, but we've collaborated on some level since product design began. The question is, what is needed to be successful? So, to answer that question, some would say that they have a process they've been using for years and it works just fine. However, the problem here that is dependent on the user's knowledge, expertise, and a variety of different tools, file transfers, email, spreadsheets, and more. So what is needed is a process that reliably automates the collaboration within the design tools, allowing the designers to focus on the task in hand and not spend time worrying about whether the other domain has the right information.
I've seen that and experienced that spiderweb-like network when you think about, especially in the Mil-Aero, when you have email, spreadsheets, the manual handoffs from Visio drawings, and the form of communication, how things are getting done and how they've been functioning. It's amazing. We continue to have success, but it's dependent on certain expertise of an individual, and it's just a very manual approach. There may be automation in some pieces of it, but overall, it's a manual spiderweb-like network. That's the best way I can describe it. And I can visualize, as you were talking, I visualize that network. How does this relate when we talk about successful PCB design, especially with the MCAD collaboration and all that you just mentioned?
Okay, just a little example. We had one customer who the mechanical team would take slices through the product every couple of mil and look at clearance analysis between electronics and mechanical, an incredibly slow and laborious process. So yes, we've moved on a lot since the days of hard copies and taking slices through. And all the time the designers are focused on making collaboration work and doing that checking, they're not concentrating on the core task in hand. Each domain needs the confidence that the other has the latest content to ensure the product development progresses in a synchronized way. Most product concepts change rapidly, especially during the early phases of a design, and electronics products are no exception. So another customer we have claims to send collaboration files, and they are using our processes here. They claim to send collaboration files between their domains multiple times a day. Can you imagine? That's a pretty extreme case, but it does highlight the need for having a reliable collaboration process. Taking the example of a product being developed and the design is nearing completion. The mechanics are in place and ready for refinement. The team are preparing for tooling quotations and concluding the design. They check back with the electronics team and a rather large component has been added some time ago that they didn't know about, that they now cannot be moved. And it collides with the mechanical housing. What now? Should the mechanical team rethink their housing design? Should the electronics team rip up their layout and accommodate the housing? The answer, of course, depends on the specific design. So there is no single answer, or is there? Having early sight of these issues through a robust collaboration process would have caught this issue early and make the change less painful. So we all bear off each other's successes.
I've seen it where the majority of times where by the time ECAD gets the data from mechanical has already started the fabrication of their housing or the envelope of where the electrical product is going to sit. And to make changes is I don't want to say it's impossible, but it's extremely costly if you're going to make a change that is going to come from the direction of ECAD or electrical. Because usually once that envelope is set, it's set. You're not adjusting that. So I agree with you in what you said about the visual of being able to have this collaboration instantly and on the fly versus waiting to the end. And then you got to go back and hopefully you caught it before you fabricated that board or assembled that board. By that point, it could be catastrophic. So Dave, tell me, is it better to source your ECAD and NCAD tools from the same vendor? And then what are the trade-offs?
Okay, better to source your ECAD and MCAD tools from the same vendor? Simple answer, yes, of course. However, it depends on where you're starting from. Changing a design tool is no small undertaking and needs to be considered carefully. Sourcing all design tools from the same vendor has huge benefits. They are, of course, guaranteed to work together, we trust. At Siemens, we spend a significant part of our planning time ensuring alignment between the different design tools in the portfolio. This also has the added benefit that new enhancements in one tool are available for use in the other. No lag while waiting for the other vendors to catch up with your latest enhancement. This alignment or combined development ensures compatibility from day one of a new version release, something that cannot be achieved when the design tools come from different vendors. So most electronic and mechanical design tools align with industry standards of collaboration, and Siemens is no exception. You mentioned IDX earlier. This ensures that if collaboration is necessary with a different vendor, you can be assured that the Siemens toolset are compliant to the standard. We don't stop there though. Within the collaboration files, we've layered in additional capability that you will get with no other tool combination. The sweet spot, this additional capability does not prevent the files from working with other tools. So we can collaborate using the same data with different tools from different vendors, and everything just works together nicely. So we understand the importance of multiple vendor tools. So the Siemens portfolio operates an open ecosystem where compatibility is supported throughout the industry standard, so customers can mix and match with confidence. This open way of working will bring good results in a robust and reliable process. However, if you want great results, invest in a portfolio from a single vendor such as Siemens for electronics, mechanical, and data management, electrical, and so on.
I couldn't agree with you more. I tell you, in my 30 years experience, I have seen multiple ecosystems, whether it's just a diverse mix of tools or what I've experienced in the last 20 years within a Siemens ecosystem. The huge return on investment being in the same ecosystem plays huge dividends, and the cohesiveness, as you said, your versions and the updates and everything that evolves, the integration is just amazing. And you're less likely to run into hiccups and stumble along the way when you're not within the same ecosystem. That doesn't mean you can't be successful, but as you said, to achieve the best success would be in the one's ecosystem as you described. And Siemens has an amazing opportunity. I'm a testament to that. 20 plus years of being in that ecosystem, whether it's within a consulting firm or a small business unit or at the enterprise level. It's amazing what Siemens bring to the table in that regard. So Dave, tell me, what are some of the latest innovations to come out of Siemens labs to help accelerate PCB design?
One of the most important things to say here is that the Siemens portfolio, the Siemens tools for mechanical and electronic design are refreshed and new enhancements come every 6 months. We're doing 2 releases per year in every single tool with monthly updates. It's a continual development there. So Greg has already commented about Mentor Graphics and how he came through into Siemens. But a few years ago, or some years ago now, Siemens invested in electronics domain by acquiring Mentor Graphics. And since the inclusion of their design tools into the portfolio, we've been making significant improvements, not only to the design capability, but to provide the most reliable and robust collaboration experience available today. So the list of recent developments, well, they're numerous. I'll discuss a few of them. Miniaturization, flexibility, and complexity all feature highly in the needs of today's designers, that's clear. Between Siemens tools, Expedition for electronics design and NX for mechanical design, you can collaborate on embedded passives, rigid board cavities, RF conductive shapes, nested cells, groups, PCB variants, and I could go on. We have introduced full collaboration capability for rigid flex designs, which is unique in the mechanical domain. Rigid flex designs are prominent in today's products. The miniaturization and the improvement in quality and reliability is a demand for that. So we've been focusing our attention there quite significantly. Also, design validation tools and methods are implemented and common across the tools. I can run a design rule analysis in the mechanical tool using the same data as they use in the electronics tool, such that both domains have the same information, and that's really important. What else? Of course, hybrid electronics. Very small miniaturization requires more connections to come out through these devices. There's just not enough real estate on the PCB, so we have the ability to use wire bonds. And NX can read and validate the collaboration data for wire bonds, showing a true 3D representation, which is pretty exciting development within the design domain. And there's more to come. We're not stopping now. We're going to continue. So just watch this space.
I couldn't agree with you more, especially when we talk about the Siemens ecosystem. And it's a lot of colleagues I have in the industry that are successful with whatever tool they're wielding. But I can say that within the Siemens ecosystem, it has, in my personal opinion, the highest potential for success if you wield that tool to its fullest advantage and take advantage of all those capabilities it has. It's amazing in the full ecosystem when you think about all the tools that come to the table, whether it's the Expedition Suite, Validate, NX, Siemens, Teamcenter, or the whole thing, Hyperlinks. It's the full suite. You're all in that ecosystem, and it's truly amazing. Our discussion today has been amazing, and I think we've outlined even our most best practices when it comes to ECAD and MCAD collaboration. I want to thank Greg and Dave again for your invaluable insight for what you shared with us today. Thanks again, you two, and make sure you keep following along with the continue of our journey, and as we cover the PCB design best practices to our audience. And please stay tuned and follow along. Greg, Dave, again, thanks again for joining and sharing your invaluable insights.
Thank you.
You're welcome. Thank you.